Okay, so today we're going to be talking about segment relationships and we're going to be proving them. And so I think the big thing is we're going to be using some of the concepts that we've been learning over the last couple of days. And because remember, proofs, we are going to be using definitions, postulates, and theorems to help us to be able to state why two segments are congruent. Now, the truth is that you're going to look at these and say, well, they just look congruent. Okay. You shouldn't judge, but we're trying to prove it, just like as if you were in a court of law. We're trying to say, yeah, I know this is true, but I have to document each step by making a statement and then stating a valid conclusion. If it's not stated clearly with those valid statements and then the reasons why, then the truth is you actually didn't show it. Okay, so we are trying to organize our thinking into logical steps so that we can show what it is. So just like when you're solving an equation in Algebra 1, and just like when we yesterday said, let's document the steps of solving an equation and saying, what did you do to do that? Well, the thing is that we are going to be doing the same thing today as we are doing these proofs, okay? So here we go. So proving segment relationships, okay? So it looks like we kind of introduced those yesterday just a little bit, okay? So some of the properties that we will be talking about would be, if you're going to be doing segment addition, you can only do segment addition if you are talking about the length of each item. Okay, and so I think the big thing is that as you're talking about adding up two shapes, okay, so let's start right down here. If you're talking about adding up two parts, you've got to be talking about the length. Okay, so you could talk about the length of this plus the length of this. And how do you know we speak of the length? Well, if it doesn't have a segment over it, that means the length between those 2 points. And so if you want to talk about proving that two segments are congruent, a lot of the time we're going to be adding up two segments to equal the entire segment. Okay, and so this entire segment PQ, and if you write PQ without a line over it, you mean the distance from P to Q. So say that PR is 2 and RQ is 5, well, then their total distance is 7. And so we may not be talking about their numbers, but if we wanted to talk about segment addition, that's something that we're going to be doing if we're trying to show that an overall segment is congruent to another overall segment. We may have to add up the parts, okay? While we're here, and one thing that we did talk about before, just a smidge, was that postulates are going to be true, okay? You don't have to show, like let me restate that, okay? We can assume that that is true, okay? A theorem, if I talk about a theorem, someone, okay, like the Pythagorean theorem, someone could prove it, okay? But since somebody already did, we can use it in our proofs and say, hey, there are theorems, but someone proved it, and so I don't have to. But theorems are things that somebody could prove, and theorems normally talk about congruence, okay? A lot of times, if you hear a theorem, it means things are congruent. So in an example would be the midpoint theorem. If C is the midpoint of segment AB, we know that AC is congruent to CB. So if this is a midpoint right here in the middle, notice we can tell that the two parts are congruent. So most of the time when you hear a theorem, we're talking about things that are congruent to each other. Not always, but I'm just saying that's a good hint. Okay. And then another thing we will be talking about would be the definition of congruent segments. If you look at two segments, okay, like segment AB, and we talk about segment like CD, if those two segments are congruent, we know that their lengths are the same, okay? And so congruency means they have the same shape and size. And so one thing we know is that if things are congruent, they have to be equal in length, okay? And vice versa. If two segments have the same length, then they will be congruent to each other. They're the same shape and size. So one thing we will use on about half of our proofs is the definition of congruent segments is, hey, guess what? If I know two segments are congruent, we know that their lengths are equal. And so, and also if two segments have equal length, they will be congruent as well. So that's a couple things that we will use quite a bit. Okay. And so I'll give you an example. It could be like AB equals CD. That means their lengths are equal. And then you could say, well, guess what I could say next? I could say segment AB is congruent to segment CD. Why? If their lengths are equal, they're going to be congruent. Now, on the other hand, if you started with the stuff on the right, if they're congruent, you could go backwards to, we know their lengths are equal. So, and the reason why you can go either way on this is by the definition of what a congruent segment means. If they're congruent, the lengths will be equal. And if the lengths are equal, the segments will be congruent. And depending what we're trying to prove, we may have to walk between those two things. Okay, let's go up to the top. Okay, so properties, okay? We're going to be dealing with some properties, okay? Property of equality, property, like lots of properties. And properties are things that are true for a set, okay? And so a set of numbers, and how shapes interact, okay? An example of that would be hang on one second. When we talk about how two segments intersect, okay, two lines intersect, they intersect at a point, okay? And so we're talking about, well, how does this go together, okay? And so some properties are like, how do different shapes interact with each other? What properties do triangles have? What properties do rectangles have, etc. And so we want to learn what those properties are because we may use them as we're trying to show something in a proof, okay? So the second thing we kind of already talked about, when would you talk about things being congruent and when would you talk about them being equal? Okay, we would use equal, okay, when we're talking about numbers, okay? When we're talking about shapes, we don't say equal, okay? You wouldn't say that two people are equal. You'd say that they're congruent if they're twins, okay? You could say their shoe sizes are equal. You could say their heights are equal. So their shapes are not equal to each other. They could be congruent, but lengths or numbers can be equal to each other. And so you could say that the length, that says length, the length of AB equals the length of CD. Maybe they're both 10 inches long, okay? You could say that the length from A to B, okay, again, if there's no segment over it means length, the length of it equals 15. So if you're talking about the length of something, you would use an equal sign, okay? So use equal when you're talking about numbers or about length or about measure, or you could even talk about like with degrees. Okay, if you're talking about an angle, you could say, hey, the measure of this angle equals 82 degrees. Okay, so an equal sign talks about somebody's measurement. Okay, you could say my height equals 5'8". You know, your shoe size equals size 9. Okay, so your numbers. The next thing I would say is that there's congruence. What does congruence mean? Congruence means that when you're talking about shapes, okay, when you're talking about a segment or an angle, okay, something that you could draw, you would say they are congruent. Okay, so shapes. So people could be congruent. So you could say AB and CD are congruent. That means that they're the same shape and same size. You could say two triangles are congruent if they're the same shape and size, okay? And so you could say shapes are congruent, but you can't say shapes are equal, okay? So that's something that we're going to kind of start talking about. Lengths are equal, okay? Numbers are equal. Shapes, people are not equal. They're congruent if they're twins, okay? The same shape and size. So today we're going to be talking about a reflexive property of congruence. We talked the other day about the reflexive property of equality, okay, where a number equals itself, okay? On this one, we're going to talk about two shapes can be congruent to each other, okay? And so, and actually this is just a shape is congruent to itself. So AB is congruent to itself. It's the same shape and size as itself. And that sounds really stupid. How we're going to use it is actually my favorite. If you've got a triangle, and if you're talking about the height of it, notice if you draw that height, notice it has two triangles, this one on the left and this one on the right, that both have that same height there. Well, whether you're talking about the left triangle, the right triangle, the height of each is still going to be the same measurement, even though it's a member of each triangle. So when you talk about two segments being a segment being congruent to itself, we're not stupid. It has to do with like when you use a segment as members of two shapes, because it's right next to each other, even if you're talking about as part of one shape or the other, it still has the same length. Okay, it's still congruent to itself. Okay, so segment AB is congruent to itself. Okay, the same shape and size as itself. Now, we do know that that means the length of AB equals the length of AB, but that's not what we're talking about. Okay, that's the property of equality. Okay, and so reflexive property of equality. So we're going to talk about, you can say two shapes are, a shape is congruent to itself. Okay, which is not that big of a deal. Reflex is kind of like when you go to the doctor and they hit your knee. That's a reflex. Okay, it's automatic. Something always equals itself. Okay, symmetric property. Okay, you're symmetric to yourself. Like if you draw a line vertically on yourself, well, the symmetric property has to do with if you write AB is congruent to CD, okay, well then guess what? You could write it the other order. CD is also congruent to AB. Okay, so just heads up, there's a symmetry. You can flip the sides of the congruent sign. The transitive property, it's like a train. Okay, so the transitive property means that if AB is congruent to CD and CD happens to be congruent to EF, well, then what we can say is that that means that they hitch up in the middle, that AB and EF are also congruent to each other. AB is congruent to EF. Okay, so you can hear the coupling of the two train cars, okay, the ones in the middle. We're swapping out like the middle, one whole side of the equation. So AB and CD are congruent and CD is congruent to EF, so therefore AB and EF are congruent to each other. So here are some properties. We're going to use some of these, so we're going to keep working on them. And the first way we're going to start working on it is to say, can you read these ones down here and tell what property is demonstrated by each of these, okay? And some of these are reviewed from yesterday. Okay, so check them out. If you start with CA plus SH equals PU plus SH, and then you end up with this, what changed? Okay, if you go to the hair place, you're like, did you notice any difference? Okay, well, if this was the start, well, what's different if you get to the second one? Well, notice the SHs are gone, aren't they? What did they do to both sides of the equation to get rid of the SHs? Well, if you thought subtract SH from both sides, that is true. Okay, so this is the subtraction property of, now is there an equal sign or a congruent sign? There's an equal sign, so you're going to say equality. Okay, so subtraction property for equal signs. Okay, when you have an equal sign, you're allowed to minus the same thing from both sides. Okay, let's check out the next one. If B is between A and C, then AC equals AB plus BC. Well, what are they actually saying? Okay, let's think about it. Point B is in between A and C. It doesn't say halfway, it just says in between. Okay, it doesn't say midpoint. Then that means the length from A to C equals the length from A to B plus the length from B to C. Okay, so what is that? Well, what is AB? AB is a segment, okay? And so the length from A to B. So we're doing segment addition. Postulate. Okay, segment addition postulate states that if you can add up the two parts of a segment and it equals the whole, okay? Because they're numbers. You add up two numbers and that equals the total distance that is from A to C. All right, and then the next one is if XY is congruent to YZ and YZ is congruent to ZA, then we know that XY and ZA are also congruent. Notice we're replacing out a whole side of the equation or congruent sign. Don't you see that? And so if you hear that XY is congruent to YZ and YZ is congruent to ZA, we have to know that XY and ZA are also congruent. You can hear a little train, okay? This is the transitive property of, is it an equal sign or a congruent sign? It's a congruent sign. Okay, so congruency or congruence. I don't care if you put a concurrency or congruence. Okay, next part. If you've got AB is congruent to CD, then we know that CD is congruent to AB. Well, that is the symmetric property of congruence. Okay, which means if you flip the sides of things that are congruent, it's still going to be true. Okay, there's a symmetric property for equal signs, and there's also a symmetric property of congruence, and this is the one that we're doing here. Now we're going to move into 3 proofs. And as we do this, I really want you to lock in and think, okay, what am I doing? What, because basically we're starting with the given. We're starting with the if. Okay, if we know that this are true, then can you show me that this has to be true? Okay. Well, the truth is we pretty much can look at the picture and know that it is true, but that's not enough. Again, in a court of law, just because you know your client is innocent, you still have to document every single step and give reasons for why you've stated every step. And so I know most of you guys won't be attorneys, but that's okay. We still have to be able to work on being logical. And that's what we're doing today. So the first step is always at least part of the given. Okay, and so they start us, and you have to document it in the proof. We know that CE and FE are congruent, and we're going to mark this on our diagram. You can use colors, or you can use like the hatch marks to be like, hey, these two are congruent to each other. Okay, whatever works for you. The other thing we know for sure is that these two segments are congruent. So EG is congruent to ED. Okay, and you can use colors, or you can use like those hatch marks to be like, hey, these two match each other as well. Okay, so, and what we want to show is that both of the bigger segments, okay, the entire segment here is congruent to this entire segment there. Okay, and so we want to show that each bigger segment is going to be congruent. Okay, so but we can tell, of course it has to be, their parts match, so therefore the whole thing does match. Okay, and that's going to be kind of our strategy, is like, hey, their pieces of the segments are actually congruent, so we know that by substitution that the bigger whole segments will be congruent as well. Okay, and so now in order to add things, we've got to talk about their length. Okay, and so the first step we're going to do is to say, well, if the two segments, like the two pink segments, CE and FE, are congruent, we know that their lengths are equal as well. Okay, and so we can say the distance from C to E is equal to the distance from F to E. Okay, so their lengths match. Okay, and we can say that the length from E to D, oopsie, hang on, is equal to the distance from E to G. Why? Because we have to add up those segments, and we can't add segments together, but we can add the lengths of the segments together. Okay, so how do we know that if the segments are congruent, that the segments have equal lengths? This is the definition of congruent segments. We talked about this in the front. If two segments are congruent, we know that means that their lengths, that they're the same shape and size. It means that their lengths will be equal as well. Okay, and so that's why we go to that. Now, again, we're going numerical. Now, what we're going to do is we're going to say that CE, okay, and I'm going to get out another color so you can see what I'm doing. The length from C to E, right, plus the length from E to D, because again, we're trying to show that the entire segments are going to be equal to each other. So I plus those two lengths together, and that will make segment CD. You see that? And then, okay, we could do the same thing for the other one, but actually this is what we're going to do. We're going to be a little sneaky, okay? Because we know above in the proof, okay, we know something sneaky. We know that CE actually is FE, right? They're equal in length. So instead of CE, guess what we're going to put? We're going to put FE. Okay, why? We're allowed to substitute things that are true. You know, if you have a $5 gift card or a $5 in your pocket, you can use either one to pay for something at that appropriate store. Okay. And then if you've got ED, well, from this one over here, try and get a nice little color. Here you go. Right here, ED and EG are equal. So instead of ED, well, the length from ED is the same as the length from EG. So I'm going to put EG as well. Okay. Why did we do that? We did some substitution. Because they're equal in value, length, we can put that other length in its place. Okay. Because they're equal. Okay. And so maybe we just show this. Be like, hey, since ED equals EG, I'm going to put EG right here. Okay. And since CE equals FE, we're going to put that right here. Okay. All right. And then FE plus EG also equals FG. Well, what are they talking about? Look at the picture. In the picture, do you see that if you add up the length from FE plus EG, what do we get? We get the distance of this light blue segment. Okay, this FG right here. Okay, and so the next thing we're going to do, because that's segment addition, you're allowed to add up the two parts of a segment together, their lengths, and equal the entire length of the segment. That's possible. That's what you do. And then notice with these two steps together, do you see that since the left sides are the same, we can do the transitive property. The order is a little weird, okay? But we notice that CD equals these two guys here, and FG equals the same stuff. So what do we know about CD and FG? They have to be equal as well. Okay, and so why? I would say actually, let's fix this because it should actually be the transitive property. Okay, that should really say the transitive property of equality because they're switching a whole side of an equation. So I don't know how that got through the cracks there, but we're going to fix that because we want to be true. A lot of kids do confuse that, and it's possible that I just didn't want to be a little bit snipey, but it's really true. It should be the transitive property. If you switch out not just one item on one side, then we call it the transitive property. We switched out the entire left side of the equation. Okay, so that makes it the transitive property, okay, of equality. And then we're going to say, okay, CD equals FG. Well, what happened there? Okay, we're trying to be sleuths and be like, okay, how did you get from step 6 to step 7? Do you see there's only one thing that changed? The order of how you said it. Okay, what allows you to flip the sides of an equation? Do you see how it kind of switched these two things? Okay, that's going to be the symmetric property. Property of equality. Because it's not a congruent sign between them. Okay. And then my next question is, how did you get from step 7 to step 8? Notice it's the same thing, but notice it says instead of saying equal, it says they're congruent. If the length from CD equals the length to FG, then we know segment CD and FG are congruent to each other. Well, do you remember? Definition of congruent segments. If two segments are equal in length, we know that we can say they're congruent and vice versa. Okay. Yeah, equal length means that they will be congruent. And so we will use the definition of congruent segments, if we're talking about segments, to say that they're equal in length and congruent. We'll do that also with angles, definition of congruent angles, and and then if they're congruent or equal. Okay, so let's try number 2. And part of this is just kind of walking with me on some of them and then bit by bit trying to think through it, engaging as we're doing this, to say, can I try to get a little better every day at these skills? Okay, so let's try this. Okay, the given is going to be a couple things. X is the midpoint of SY. The other given is Z is the midpoint of YF. And then the third given is XY and YZ are equal in length. Okay, so there's 3 things. Now, you sometimes write all the givens within the first step or 2 of your proof, but sometimes, like an attorney who's very tricky, you might wait to hold off on some information till later on in the proof until it makes more sense or for a more dramatic moment in the courtroom. Okay, so let's write down what we know. X is the midpoint of SY. Okay, we also know that Z is the midpoint of YF. We also know that XY, okay, is equal in length to YZ. Okay, so there you go. We know 3 things. We got a midpoint, we got another midpoint, and then we've got 2 segments that are congruent. And our hope is to prove that, what is it? What do we want to prove? We want to prove that ZF and SX are congruent. And ZF is this. We want to prove that it's congruent to SX. And so that should be our last thing. So let's write that down as our last step, okay? So we'd say ZF is congruent to SX, sorry. Okay, so we don't know why, but we know we're going to say that at the end. Just like you're like, I know my client is innocent. Okay, that's that's going to be our last thing that we say. Okay, so we can kind of tell that there's a lot of stuff that's going on. We can kind of see like, yes, for sure they look like they're congruent. Okay, we just have to document each step so that we can say competently, and here is why. I documented every step. So we're going to walk through this together. So start with one of the givens. Okay, X is the midpoint of SY. So we're going to check that off. We used it, and that's given. Why did you come up with that? That's the if part. The givens are the ifs. Then the conclusion is going to be at the bottom. Okay, so that's given. Now got a question. If we know that X is the midpoint of SY, then we learned a couple days ago, okay, and again, we're kind of putting these all together. So if I scroll back in my notes and be like, okay, what did we learn? We talked about, where is this little thing? It was a couple days ago. Okay, midpoint theorem. Here we go. The midpoint theorem states that if X is the midpoint of AB, then these two segments are congruent. Okay, so we can say, hey, I know that X is the midpoint of AB, then I'm allowed to say that the two pieces are congruent to each other. Why? The midpoint theorem. Theorems tend to say that things are congruent. Okay, so the midpoint theorem is if you have a midpoint, the two parts are congruent. Okay, so let's do that. So our second step is this. If X happens to be the midpoint, okay, right here, if X is the midpoint of that segment, then we know that the two parts here have to be congruent to each other. And so we're going to say SX and XY are congruent to each other. Why? The midpoint theorem. I have a midpoint. I know the parts are congruent. Okay. Now we're starting to see, hey, guess what? There's a lot of stuff that's congruent. So the next thing that was given was that Z happens to be the midpoint of this other segment. Okay, that's given. And then what do we know as a result? Midpoints cut things in half, right? So who is congruent? We're going to say that YZ is congruent. Segment YZ is congruent, same shape and size as ZF. Why? Because that's what midpoints do. It's the midpoint theorem. So we know that these two segments are congruent to each other. Okay. Okay, the next thing is this. Okay, we've got to bring together steps 2 and 4. Because we're going to end up adding some segments together, okay? We're going to end up adding some segments together, or we're going to start talking about their lengths. So therefore, we're going to say, okay, if these two are congruent, then we're going to say we know that they're equal in length, okay? Oh, wait, right here. Okay, and then we're going to say this right here. If these two are congruent, we know that those are equal in length as well, okay? What tells us that if things are congruent, that they'll have equal lengths as well? Well, that's what congruency means. It's a definition of congruent, and it's not an angle, it's a segment. So definition of congruent segments. If they're congruent, that means their lengths will be equal, okay? The next thing is going to be a given, okay? We're waiting for that dramatic moment to use it now. We know that XY is equal to YZ. We know those two parts are equal in length, and that's given, okay? Now we're going to do a transitive property, okay? And it's going to be a little bit piecey to put it together. So watch this. If we've got, I'm looking at my notes to be like, okay, why are we doing this? Let's think about it. Can we see kind of up above where we're heading? Okay. Okay, here we go. If you know that SX equals XY, and we know that XY equals YZ, if we put these together, what do we know? SX and YZ are going to be equal in length to each other. Why? The transitive property. of equality. And then, so notice we're swapping out this side of the equation, the XY part, okay? And then we're gonna do it again, okay? We're gonna say, I'm gonna grab a different color. The other thing we're gonna do is if we know that YZ, okay, is equal to ZF, okay? And then we know that this is YZ here. So we're gonna take this and this together. Okay, so notice they both have YZ. So if YZs are the same, well then guess what's gonna happen? We're gonna say SX has to equal ZF as well. So you gotta kind of watch these are tricky. You're kind of looking to say, can I see this clues? This is something that we're not ready to do by ourselves completely, but we're gonna get better as we do it. So we're gonna put those together and we're gonna get this. And then this is ZF. Okay, and then we're basically there. Okay, SX and ZF, we have to switch the order because look at the answer. The answer is in a specific order. Okay, they have those two things we've got, but the order is different. And also the thing is that we need to say they're congruent. Okay, so we're going to say SX is congruent to ZF. Why? Definition of congruent segments. And you're allowed to abbreviate congruent segments there if you need to. And then what did we do to get from 9 to 10? We did the symmetric property of congruence. So that's a lot of steps, okay? And so we're just trying to recognize some of the steps you could come up with to be like, hey, that to go from here to here is pretty straightforward. To go from here to here is pretty straightforward. This part in the middle where we're doing the transitive property, probably you need your hand held a little bit, okay? Another thing is, could you go from here to here and say, yes, I did the definition of congruent segments to go from equal to congruent. And then could I go from here to here, talking about, can I just flip the sides of a problem, okay? And you can do the symmetric property for an equation or a congruent sign. So yeah, we're getting like big kids, okay? This is a good thing. Okay, we got one more to do. Okay, the next one says, given GJ is congruent to GI. So GJ and GI are congruent, okay? Also, K happens to be the midpoint of this side, okay? And H happens to be the midpoint of that side, okay? So we got a lot of good stuff they came up with. So we're gonna start with K is the midpoint of GJ and H is the midpoint of this. How dare we say that? Well, those are both givens, okay? So I'm gonna check them off our list. Those are given, okay? Okay, got a question. If you have a midpoint, what happens to the two pieces on that side? If you have a midpoint, the two pieces have to be congruent to each other. So on each side, these two parts will match each other, and then these two parts will be congruent to each other. Why? The midpoint theorem. Okay, now I got a question. What do you think we can say if we know that things are congruent? If two segments are congruent, what's true about their lengths? Well, their lengths are equal in measure, so we can do that. So those two sides have two pieces that are equal in length to each other, okay? And that's the definition of congruent segments. If segments are congruent, they will be equal in length and vice versa, okay? The next thing, GJ and GI are congruent. Well, that was a given, okay? So again, like the surprise moment, we're like, I didn't say it all up top, okay? So these two should be from the givens, okay, right here. And that is given. And then another thing is this, our goal is to show, okay, this right here, we want to show that GK and GH are going to be the same length. Whereas GK and GK is here and GH is here. Nope, lies. GH is right here. Okay, so we want to show that those two are congruent to each other. And notice that's the last step that we write. Okay, wait, I don't know what the reason is. We'll get to that. Okay, so we know that there's midpoints. It breaks up into two congruent pieces. We know that because they're congruent, the segments are equal. Another thing here, how do you get from here to here? If two segments are congruent, we know that their lengths are equal. Why? Definition of congruent segments. Okay, the next one. Looks like we're adding. How do you get from G to J? Well, you add up the length from G to K and the length from K to J. How do you get from G to I? You take G to H and you add up H to I. How can you do that? That is segment addition postulate. Okay, you're allowed to add the lengths of two segments together to equal the total segment. Okay. And then the question is, what are we doing next? Okay, look at this. Do you see right here? Okay. And then you see right below GJ, and you see below here GI. In place of GJ, guess what we're going to do? We are going to say, since GJ equals this, let's, in place of GJ, let's put that. Okay, so I'm going to put it instead of GJ right here. So we're putting it right there. And then since GI actually equals these two things right here, so in this equation here, I'm going to put this stuff right here. So that's the transitive property, okay? Okay, so you're swapping out a whole side, so it's a transitive property. Okay. And then the next question is, I went from, and sometimes it's just you ask like, what did I do to get from this step to this step? Do you notice what's different? I notice that this is different. I also notice that this is different. How come I put KJ, instead I put KJ, I put GK? How come? Well, look up here. We must know that these two are equal. Okay, let's look and see if there's a spot there. Oh, right here in step 3. And then also, do you see that this right here, HI is now GH? Well, we must know, from step 3, that GH and HI are equal in length. Okay, so guess what? We're going to do a substitution. Since we're just swapping out one term on one side, not a whole side, it's substitution. Okay. And the next one says 2GK equals 2G. Okay, what they're doing is if you have 2 GKs added together, you get 2 GKs. If you had 2 GHs together, you get 2 GHs. So they're just combining like terms. Or simplify, that's fine. The last one is, let's divide both sides by 2. Division. Property of equality. And then the last one, how do you get from here to here? If 2 lengths are equal, okay, what do we know? They're all the segments will be congruent. Okay, this should have a congruency sign over it. Okay, just like it does up here. And so this is definition of congruent segments. All right, well, there we go. That was a big day, wasn't it? We talked about some of the properties. We talked about how could we document our steps. Thank you so much. I hope you have a tremendous day.